All right, so this video is going to be on the conversion of alcohols to alkyl halides with HX, so HCl, HBr, and HI. Okay. Now, before we get into that, I want to kind of remind you what we went over in the past, which was, let's say, this cyclohexanol with sulfuric acid gives you an alkene and water, right, as well as that sulfuric acid back. So the thing about this particular molecule is that after we protonate with that sulfuric acid, we get an oxonium ion. So that oxygen wants to be neutralized, right? It's got that positive charge. And it does that by leaving as water. And so what we get is a carbocation intermediate. Now this carbocation intermediate can then do a couple things, right? We've seen it before, and so we can do beta hydride elimination, or beta hydrogen elimination. Let me make that in blue, where a base comes along and swoops on it. You make that double bond, or a nucleophile can come along. That's an SN1 reaction, right? The elimination would be an E1 reaction. Now, that's exactly, the nucleophile attacking is exactly what this chapter is all about, or this section's all about. And it's kind of a clever way to do it because we have a source of a nucleophile and an acid in one when we use HCl, HBr, and HI. So protonate, just like before, we get that oxonium ion. That oxonium, or the water, wants to leave, forming that carbocation intermediate. And that chloride that was the counter anion is now the nucleophile and can attack. Okay, so remember, chloride, bromide, and iodide are also decent nucleophiles, and so we get that chlorine substituting for that OH group. And that's exactly the chapter, or the section. So you're done. That's it. All right, just kidding. No, well, now we got a couple things that we want to talk about in addition to that, but we already know this stuff. It's so, that's what I'm saying. Like, if we focused on 6, 7, and 8, then you guys you're good to go. This is easy stuff for you. It's just kind of a refresher, but also looking at it in a different way. Okay, so it's always about how can we make it a good leaving group, and then where's a nucleophile or anything like that. So anytime you have an acid, you probably want to protonate something, and then make sure you draw that counter or the conjugate base, so that way you know if it's going to be a weak base or a good, or a weak nucleophile or a good nucleophile. Okay, so in this case we have well, let me just draw this out right here. But this particular alkene product right here was at via E2 or E1, right? So as we go from left to right, from primary to tertiary, we get an increased rate of reaction with HX. Okay, and similar to the dehydration reaction, we could have E1 or E2. Well, in this one, we can have SN1 or SN2. So if it's primary, then we're going to go via the SN2 route. If it's secondary or tertiary, we're going to go the SN1 route. Okay, so you guys know this already, because when you protonate an OH group and you have that carbocation intermediate, or I'm sorry, the oxonium intermediate, and it wants to leave, can it leave is the question, right? If it can leave, then it's an SN1. If it can't, then it's SN2. But the question really is, can you form that carbocation intermediate? And in this case, you can, because it's tertiary. That chloride can come along and attack to form that new alkyl halide via an SN1 reaction. Okay, so that was a tertiary alcohol, and so that's why we can do this. Okay, and so that's really what we mean. This one right here was a secondary, and that also went via an SN1 reaction. Okay, so what does it look like when we have a primary or like a methyl substituent? Well, let's take a look at ethanol as an example. You can use HCl, HBr, or HI, right? Just, we've already mentioned that. And if we go the SN2 route, we're going to get that substitution of X, right? But the question, or the important thing to note, is that I'm terrible at drawing arrows, but also that the rate of reactivity, or the rate of reactivity is going to go from HCl down to HBr down to HI. Okay, so we have, sorry, not an increased rate of SN2, but just the increased reactivity, of SN2 in a polar protic solvent, right? So that's because iodide is going to be our conjugate base, which is the source of that nucleophile, and iodide is a stronger nucleophile in polar protic solvents, right? And that's because it's larger and more polarizable. Help me polarize, help me polarize, help me. Y'all know about 21 Pilots? All right, so that's all I always think about that. Anytime I hear about polarization or polarizability. Ethanol attacks the oxygen, the most basic site, attacks the proton, making the oxonium ion. That water can't leave because we can't form that methyl cation, but the iodide can attack. Backside attack via SN2, and we get, I drew the wedges and the dashes just because it's technically inversion, right? Because it's an SN2, but it's only inversion, or it's only obvious that there's an inversion occurring when there is a stereogenic center. So if it's chiral, right? So otherwise, the hydrogens, two hydrogens, you can't tell. It's indistinguishable. But via the SN1 reaction, remember, a racemization occurs if it is chiral. That means that's because we have that planar carbocation intermediate. Okay, so this particular mechanism for SN2 with HI and HBr is going to be the same, but HCl is lame. Okay, so it requires a little bit extra, and so it requires a zinc chloride addition or added Lewis acid catalyst. Okay, so zinc chloride is a Lewis acid, meaning it can accept electrons. If it can accept electrons, where's it going to get it from? Well, the most electron dense atom is the oxygen. It's the Lewis base also, right? So you attack the zinc chloride. You get this oxonium intermediate again with a negative charge on that zinc. Now, what we want to do is backside attack with the chloride and force that to leave. What we get is the same product, but we also have just a different leaving group. This is zinc chloride with the OH on there and a negative charge. Okay, so the thing here is the presence of the zinc actually just kind of, it's a Lewis acid, so it pulls on that oxygen, kind of decreasing the bond strength of that carbon-oxygen bond, and so that's why it helps this process move forward, because chloride in polar protic solvents is not a very good nucleophile, and so we need a little bit extra help. Okay, and you're still adding that HCl in this case. Okay, that's your source of the chloride. Another thing I want to add real quick is, if it wasn't obvious why this is a polar protic solvent for the reaction, it's because the alcohol is polar protic, right? So now this particular example, right, what do we have here? We got HBr, so we know, and we got an alcohol. Now we got that hydrogen as a wedge. I'm sorry, the dash. Now this particular carbon right here, this is technically, it looks kind of confusing, right? It's technically primary because that D is deuterium, which is a hydrogen isotope. And so what we want to look for on the primary is inversion via SN2. So of course, strong acid in the presence of a base is going to protonate that base, get that oxonium intermediate. Now that does want to leave, but it can't. So we're going to force it out by attack of that nucleophile via the backside. And that results in your umbrella flipping inside out. Pissed, right? And so your wedge and dash are still more or less the same direction. They're both up and down, and then the deuterium is down, but they're projected the opposite way, as if you inverted your umbrella, right? And so that's one way you can draw it. Another way you can draw it is actually just keep the geometry the same. So notice it's the same orientation as the original molecule. We just substituted the bromine for the OH. But what you do is you swap the wedge and the dash substituent. So instead of the hydrogen being a dash, it's on the wedge. And instead of the methyl being on the wedge, it's on the dash. They are the same molecule. You just have to rotate them and flip them 180 degrees, and they are the same. I encourage you to check that out to prove to yourself with a modeling kit or just on paper. Okay. Now this particular molecule right here, that is a tertiary alcohol, right? And so now what we're thinking is HCl on a tertiary alcohol. We got SN1. And what that means is we're going to get the retention of stereochemistry as well as inversion of stereochemistry because of that carbocation intermediate. So what I do is just draw the same molecule, draw the wedge in the dash, substitute the nucleophile with the OH, and then also draw it again, but switch the chloride essentially for the not on the dash now, but on the wedge. Okay, the top is retention of stereochemistry because the chlorine is in the same position as the original OH, and then inversion is when it's no longer on the dash position but on a wedge. Okay, so moving on, we've got carbocation rearrangements, of course, right? Anytime you have a carbocation forming, so that SN1, so this is only going to be applying to the secondary and tertiary, we can potentially form rearrangements, right? But again, remember the purpose of these rearrangements is to make it a more stable carbocation, and so it really only applies to those secondary alcohols, right? Because if we have a tertiary carbocation from a tertiary alcohol, then we don't need to form those rearrangements. Now, if a question asks you like, well, how did you get to this, and it was clearly a rearrangement, then of course you know what to do. Okay, so we have that 1,2 hydride shift that we saw before with the alcohol and sulfuric acid, right? And that gave you your tertiary carbocation, which then allowed you to form that more substituted alkene product, right? Okay, so let's say we had, instead of sulfuric acid, we had HBr. Well, we know that secondary alcohol with HBr protonate that OH, and then after, I'm going to draw two arrows because we do the same mechanism essentially to get to that same exact carbocation, okay? Now, instead of having a weak base present, we have a decent nucleophile that can attack that carbocation intermediate, forming the alkyl bromide, the tertiary alkyl bromide, okay? Now, we do not form the secondary alkyl bromide because that rearrangement is so easy for the hydrogen to just swoop on over and form that more stable carbocation intermediate. Okay, so let's say we had this guy, this secondary alcohol again with HCl instead. Okay, remember we don't need the zinc chloride with HCl unless we have a primary alcohol, so that's irrelevant here. That we form that oxonium intermediate. This is a secondary alcohol, so it can leave, and we form a secondary carbocation. Okay, we want to can stabilize it, we want to stabilize that, and so in this case, it's not a 1,2 hydride shift, but a 1,2 alkyl shift because we have a methyl directly adjacent to it, and the shift of that 1,2 alkyl shift will result in a tertiary carbocation, which is more stable. Okay, don't forget about that chloride being there. Boom, comes along, attacks that carbocation, and now we've got this new alkyl halide, which I drew really weird. Let me make sure all the carbons are there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we're cool. Sorry, I drew it weird. Those bond angles, oh my goodness, don't do that. I gotta lead by example, but I'm gonna move on. Okay, you know those bond angles are just ridiculous, right? So conversion of alcohols to alkyl halides using a couple other things. Okay, so what we're going to use is SOCl2 and PBr3. Okay, and then that's SOCl2 is thionyl chloride, and then PBr3 is phosphorus tribromide. So we have, this is going to be done with primary and secondary alcohols. Okay, so when we have thionyl chloride, we'll make the alkyl chloride, and when we have the PBr3, we will make the alkyl, what do you think? Bromide. Yes, indeed. Yes, indeed. So that, again, remember, is primary or secondary alcohols only. Why do you think that might be? What substitution reaction can you only do with primary and secondary alcohols? It's an SN2 reaction mechanism, right? And so this is really what you want to gather from this particular section is the mechanism. it's very easy to just go from ROH to RCl, right? Or ROH to RBr, okay? But the mechanism is really what you want. Oh, shoot, I gotta put that pyridine in there. Okay, so the alcohol attacks the sulfur, kicks that pi electron up, then that comes back down, and it forces that chlorine to leave. Okay, so what we end up getting is we still have this oxonium intermediate with we lost a chlorine though. Okay, don't forget about that chlorine. He's coming back later. Okay, so the pyridine, the presence of that, remember pyridine is a good base. And so what it does is it neutralizes that oxygen by removing that proton. And we've got this here molecule, okay? Now we've also got a pyridinium ion, right? That a pyridine with a proton on it, positively charged. So, so that chlorine that left, we can kind of draw that there. We can also draw it here. And what it does is it attacks that carbon, backside attack, right? It's an SN2 mechanism. Backside attack of that carbon that kicks out the oxygen sulfur group. But when it does that, it creates a pi bond between oxygen and sulfur, making and then that forces the chloride to leave. So you end up with a chloride as chloride ion, and then SO2 gas, and then the alkyl chloride product. So SO2 gas is leaving as a gas, and so that's actually driving this reaction forward as well, right? So that's why this is such a good leaving group. Anytime you can form a gas to leave, then it's an amazing leaving group, okay? And so this is going to occur with primary or secondary alcohols, remember? And that's because it is an SN2 reaction. So that backside attack won't occur on a tertiary alkyl group, essentially. So now we've got this alcohol with PBr3 goes to an alkyl bromide. Okay, so let's take a look. I did a primary alcohol before, so let's do a secondary alcohol on this one, just as an example. I think you know this stuff by now though, right? The only thing you need to know, you know the general idea, but the mechanism behind it is a little bit different because we have this oxygen attacking the phosphorus. That kicks out that bromine because we don't have any pi bonds to shuffle around. Then what we get is this oxonium with the PBr2 now, and then that bromide that got kicked out is the source of our nucleophile. And so we don't have pyridine present in this one. And so what happens is it just kicks it right along, and we get the substitution with our bromine, so we get our alkyl bromide product. Awesome. That's what we wanted. And we also get this HOPBr2, okay? One thing to help you remember this, hopefully, is phosphorus and oxygen have a strong affinity for one another, and so you always want to form a phosphorus-oxygen bond if you can. And so you'll see this again later with something called a Wittig reaction, but again, this works well with the primary or secondary alcohols, okay? Now you might be wondering, why are we doing this, right? Well, it's more tools in our toolbox, okay? So we have an alcohol, that's not a good leaving group, and it limits our ability to kind of substitute that carbon with something else. But we do know that alkyl halides can do a variety of things like elimination reactions and nucleophilic substitution. And so that's really all we're doing here is kind of finding different routes to make new carbon-carbon bonds. And that's all about organic synthesis. And that's really what this class is all about, is create a very large toolbox to create new organic molecules, okay? So that's pretty much it. Let me know if you have some questions. I know we went fast, but this was more or less a review, and so I really want you to just kind of focus on those mechanisms, and then understand that anytime you have a base present, like an alcohol, in the presence of an acid, you probably want to protonate that, right? Or if you have a Lewis acid and a Lewis base, you probably want to bring those together too. So that's your first step. Anytime you see something like that, you want to do that, draw the next thing that would form, and then go from there. Okay, it's really important that you understand these mechanisms, because we will start to use these reagents again, or will use similar looking reagents that might confuse you, but if you understand the mechanism behind it, then it won't confuse you, and you won't see those reagents and then think like, oh crap, well, like what reaction was that? So focus on those mechanisms that I drew, and you should be good to go. All right, have fun with it. Also, let's play a game of Find the Doodle. Doesn't my dog look like leaves? Oh, he's also adorable. So you're welcome.